Okay, want to go into reflection a little bit more and then talk about refraction and diffraction, other important wave behaviors. So first off, light behaves like a ball that's rolled and hits a wall. So it bounces off at an angle equal to that of the that it struck at. Okay, so if this angle right here is 20 degrees, then this angle right here would be 20 degrees. And it's usually measured to a normal line, or aka a line that's perpendicular to the surface. So that if there's a curved surface, you can go normal to the tangent and that sort of thing. So a light beam reflects off the same way at an angle equal to that of the reflection. So this is normally stated as the angle of incidence. Remember, the incident is the wave that you send. Is equal to the angle of the reflection, where the angles are measured from the beam of light to a line that's normal to the surface, perpendicular to the surface. So that is the law of reflection. So again, the reason they don't use just use this angle here and measure it to the surface is, let's say you've got a curved surface, and let's say the curves aren't even the same on both sides. So it's always measured to the tangent. Okay, when we start talking about refraction and that sort of and diffraction, we need to be able to represent a wave in a kind of a simple method. So to represent a circular wave, what we'll do is just represent these circles as let's say crests that are radiating out in all directions. So these are the wave fronts. Okay, the crests, and they're radiating out in all directions. So, so if you go perpendicular to the line of the wave front, that shows the direction of travel of the wave. So perpendicular to the tangent here. Okay, so. Sometimes they make these large they have these large wave pools to test things like how well boats maintain stability in high wave situations and things like that. There are a lot of different things in a wave pool. So this is an example of a wave tank, and here they're oscillating this thing back and forth, creating these linear waves in this tank. And the waves are traveling to the right in this case. So here we've got probably a very expensive towboat that's being tested for its seaworthiness. Now, when we talk about reflection, the angle of incidence is equal to the angle of refraction. So if I measure the angle equal to my or against my perpendicular line, this looks like it'll be 45 degrees in both cases. So if I have my perpendicular line, 45 degrees, that sort of thing. If it's not 45 degrees, it doesn't matter. The angles just have to be the same. So if this angle opens up a little bit, then this angle will open up some too, to match it, as long as the angles are equal. So here we've got a wave that's coming and then it's reflecting off. Wherever you see waves overlap, you're going to see constructive or destructive interference. You're going to see some interference. So where the lines cross, you can expect to see a crest and a crest, and then you're going to see constructive interference, and then it looks like there'll also be a trough and a trough overlapping as well. So you're going to see constructive interference in this thing. What would that look like, constructive and constructive interference on a wave like this? Well, it's going to look a little bit like an egg carton, where here you've got the high points and here you've got the low points. Let me show you what that would look like in 3D. So here you've got the waves coming and they're entering into this medium. The key thing here is that they're reflecting off this boundary, and the waves are continuing to come down. So you're getting constructive interference of the waves. So anyway, that's that. Okay. So when a wave meets a boundary, two things are going to happen where it changes speed. One is it's going to change wavelength, and the other is its velocity is going to change and its wavelength is going to change. Yeah. Okay. So in the transmitted pulse, the reflected pulse, the wavelength and frequency and speed are going to remain the same. But in the transmitted pulse, if it slows down, the wave should get a little shorter in that. So what we're going to do is we're going to look at switching into a new medium. And so here we've got water waves, and they're going to go over a shallow region where they slow down. Okay, where they slow down, V equals lambda F. If V goes down in frequency, the frequency stays the same because this is still beating into this medium with a certain frequency, whatever frequency is being beat into the medium over here. But notice that the waves get shorter. They reach into the new medium. So this is what happens as waves come crashing to the shore from the deep ocean. They get shallower and more narrow, and they start to break and that kind of thing. Okay, if they hit straight on, they hit on a boundary that's straight on. This is just what you see. But when they meet a boundary at an angle, then something interesting happens. So this is the incident wave coming in like this. So traveling to the right. Okay, how would you draw that velocity of the wave for the wave down here? It looks like it's probably moving along the lines of like that. Okay, so this is said to be refracted. So this is refraction. When a wave enters a new medium and slows down and changes direction. Okay, that's refraction. When a wave enters a new medium and changes speed, probably not just slows down, changes speed is the better way of saying that. Changes speed and changes direction or bends. Okay, so there's a couple different ways that you can look at this. One is that the only way for the wave fronts to remain connected in the new medium is for them to bend. Okay, so notice how these lines are still connected, okay, and they're not jaggedly detached. Okay, the only way for that to happen is for this medium to curve around a little bit, or not the medium, but the waves to make that turn. So this is showing you like this. So because the waves are shorter, okay, if the wave didn't bend, then the wave fronts would be disconnected. Okay, in order for them to remain connected, they've got to make this turn in order to stay aligned. Okay, so let's take a look at that. So here I'm back at that ripple tank. So what I want to do so let's take a look at this wave. This wave has a source frequency of 4 hertz. I'm guessing, although it looks a little slower than that. And so if I clear the waves, you can see the wave front move with some velocity. So there's some velocity in meters per second that this wave is moving, and it's got a wavelength based on its frequency, well, and that velocity. So now what I want to do is increase the frequency. So if I increase the frequency, what's going to happen to my wavelength? Now I've doubled the frequency. You can see that my wavelength has decreased. As a matter of fact, it's half of what it was before. And now what happened to the velocity when I changed the wavelength? Okay, well, the velocity didn't change. The wave fronts here are still moving at the exact same rate they were moving when they were back here. So remember, frequency and wavelength don't affect speed, but speed can affect frequency and wavelength. Well, not frequency, but not in normally anyway. So anyway, that's that. So there's another way to look at and an easy way to remember which way light will bend when it meets a surface. So I guess I really should have had a picture of light refraction, of light bending. So picture yourself looking at the straw in a cup of water, where the straw looks like it's disconnected from the straw in the water. So that's a common example of refraction, but that's because light makes a turn when it meets a new medium. So so here we've got a sled, and the sled is going to represent our beam of light, or it could be sound, or it could be an ocean wave, or it could be whatever. Then this represents our new medium. So here we're going from ice into mud. And so what I want you to do is we're going to look at this sled. Okay, now when it meets this mud at an angle, it's going to slow down where it contacts the mud. Okay, so it means this rail is going to be moving slower than this rail. Okay, so which way is that going to cause it to turn? That's going to cause it to turn right. Okay, so you can take your hand and kind of form it into a C shape, and use that to represent the rails. Which one is going to which rail is going to slow down or speed up, and what's that going to do to the motion of the sled? So anyway, this is probably the easiest way to think about refraction, which is the bending of light. So there we go. So now let's say we approach it from this angle. So which way is it going to bend now? Is it going to bend up or down? Okay. Well, if you take your hand, this would be a lot easier if we were together in the C shape, and then so the part of your hand that meets the mud first is going to stick, and the other part of your hand is going to keep rotating. So it's going to curve up. Okay. So it's going to curve up. Okay. Now, what if it hits head on? Okay. Well, both rails are going to slow down at the same time, so it'll just go straight. Okay. So now, how will it turn when it leaves the mud? So let's say it speeds up when it leaves the mud and gets back on the ice. So we have to picture it as being self-propelled, I suppose. So here it's going to curve to the right. Okay, and then now the rail that exited the ice, okay, is going to speed up. So that means that the upper one here, and then there's the one that's still in the ice here. I wonder if I can stop that in some way. I guess I could do this. So so this rail is going to speed up, which means this rail is going to stay moving slowly. That's going to cause this to curve to the left. Okay, so so that's that. Okay. Whoa. So here we've got some more examples of waves, water waves refracting. So here, what happens to the waves speed in each picture? So let's say these are the waves we're sending. Okay, so if we look at this, okay, the waves got shorter, so that must mean it's moving more slowly. And if you picture taking your hand along, meeting that boundary, having your finger that left the boundary like stop and pivot, and then curve to the right. Okay, yeah, curve to the right. This would be so much easier if we were in person. So here we've got it's speeding up, so the opposite direction is occurring. So here they notice that the waves get a little further apart, the wavelength increases. So that's what happens when the frequency stays the same and the velocity increases. Okay, so these are just pictures of kind of what we'd seen. So slow waves, and then fast waves. Okay, and the last one, which is pretty simple, we're not going to get into it too deep, is called diffraction. And basically, when a wave meets a boundary or an obstruction, I guess is a better way of saying that, it bends around that disruption. So here the water wave is going through this opening where we've got these two rocks as the disruption. And it looks like you can see these circular waves that are resulting from that. So basically, it's when water meets an opening, it acts as if the wave was being generated at that opening. So it's like somebody was tapping their finger in the water here. So here we've got linear wave fronts. And then when they meet this this opening, it acts like the wave is being generated from this point, and we get these circular patterns. So this is a very common picture of diffraction. So the bending of wave around an obstruction. So and when you've got an opening, you get that circular wave pattern. Okay. So this is another example of diffraction. So here you've got your opening, and then you've got your circular waves. Okay. Another example here, we've got an opening, and we've got our circular waves. So very, very common. Light does this too. Sound does this too. So all waves exhibit this behavior. The closer the slit is to the wavelength, the more it behaves like a point source at that opening. So when it's a much wider opening, the diffraction effect isn't as noticeable. Okay. Let's say I created I set up an experiment. I had linear wave fronts reaching an opening. Then we have these this diffraction going on here, and then it meets two slits, two openings. Okay. So we're going to have it's going to look like a wave is being generated here, and it's going to look like a wave is being generated here. Okay. So where, and this is, and light does this. This is the wall, so we're going to have constructive interference where these intersect, okay, and at the center of the whites, okay, and we're going to have destructive interference along the lines where it's not an intersection. And what you're going to see is along the wall there's going to be high points and low points, from constructive interference to destructive interference to constructive interference to destructive interference. And you can actually do this with light. It's a famous experiment called the double slit experiment. And you'll actually get light waves where they add up on certain regions and it's bright. And you can actually have light cancel out another beam of light, another photon of light. Which is pretty crazy to think that you can cancel out one beam of light with another beam of light. But you can do it, at least in some controlled circumstances. So, okay. All right, that's it for today, and good luck with the problems.